Hello and welcome on top of the RV research vessel Pelagia, sailing through the subtropical Northeast Atlantic Ocean on our way from Canary Islands to the EEZ, just outside the EEZ of the Cabo Verde Islands. South, sailing south. And as you can see, take some time to look around. You see the radar. We're not affected by it, fortunately. It's a bit choppy sea. You see some what we call heads on the waves. So we have wind force 4 to 5. It's a bit wobbly here because we're on the highest point of the ship, so the most amplitude. And what we do here, we study Saharan dust that is blowing from the African continent towards the west through the trades. My name is Dust2025. I'm a marine geologist at NIOS, the Royal Netherlands Institute for Sea Research. And one day a week I have a position at the VU, Vrije Universiteit Amsterdam, where I have a chair in aeolian sedimentology, which is basically any sediments blowing through the air, mostly dust, of course. And why do we study dust? It's been recognized that the dust actually plays many roles in the Earth's climate. And there's a lot we don't know yet. For example, energy from the sun is being reflected by dust, but also so that acts as a cooling effect, but also dust can absorb heat, so working as a greenhouse gas. There are ideas about how dust can fertilize the ocean, leading to eventually a reduction in CO2, another greenhouse gas. There's relationships with methane as well. Dust and sea salt together can make sure that the methane is decomposed, so another removal of another greenhouse gas. And actually this is a relatively new field of studies, so more and more disciplines are joining in and finding new exciting results. So why are we here on the top deck? Here we have the most free airflow, let's say, and this is where we collect the dust with these two mailbox-like pieces of equipment, so-called high-volume dust collectors. Basically, there's a vacuum cleaner engine, Miele or Nilfisk or Dyson or what have you, pumping air through a filter, which is below this triangular hood. Air can pass from all four sides below the hood, is sucked into the filter, and the particles remain on the filter, so we can study them. For example, for the grain size, for the mineralogy, the chemistry, grain shape. All these characteristics play a role in the role that dust plays in climate. So there's all kinds of sorting trends in a spatial sense as well as in a vertical sense. You can imagine there's different ways in dust can be deposited on the ocean, just by gravity or by falling in with precipitation, with rain. And we hardly know anything about this. So we try to study this and also from a geological perspective try to relate the dust that we find on the sea floor and in sea floor sediment core archives as well as ice core archives, for example. Try to relate those characteristics to, for example, wind strength, climate, how dry was it, how much dust was produced, how much dispersed along the wind patterns. So here we are on top deck. I'll take you down below to the other labs to show you some more instruments, but these are now the dust collectors. At the moment they're switched off because should they be working they would make a hell of a noise. But actually, as you can see, in the wind vane, the wind is coming from the back, meaning that material from the chimney could potentially contaminate our filters. So we don't want that. Machines are only on when the wind is from a given direction up front. Just behind the lights, probably cannot see it, there's also a rain sensor. So if it's raining, we don't want to have these machines on because air with water sucked into the machine is not a good idea. I hope that was clear, and let's go downstairs. So, welcome in the wet lab. Just before we were upstairs with the dust collectors. This is the so-called wet lab. Take a moment to look around you. It's all open, so literally the sea can come in and flush it, but we also, if we spill something here, it can easily be washed out. And this is where most of the wet stuff, the waterworks, are done. And there's also ways to collect dust with the traps in the ocean. And one way is the so-called drifting traps, which is a set of 3 of these frames in which we put a tube, open tube. So we have 4 of these tubes at each depth, mostly at 100, 200 and 400 meters. They drift freely, and as you saw maybe in the frame makes sure, and the weight in the tube makes sure that they're always vertically oriented. So material from the sea can settle in. And this contains dust, obviously. But we're also interested in the marine environmental effects of this dust. So is it really true that the dust provides nutrients to the ocean, phytoplankton? Does it respond to this dust? And does it indeed sequester CO2 in the end from the atmosphere? That's what we want to know. And this is one way, because the organic matter that's produced by, for example, phytoplankton and then is sinking to the sea floor never does so as a single particle. It's always some kind of aggregation, what we call marine snow. And this marine snow is very fragile, so if you touch it, it will already fall apart. Now, in these tubes, these marine snow particles, they settle, and we can filter them, so we have a bulk amount of marine snow. But also, we have an option to put a petri dish in here with gel, in which the marine snow particles sink and are preserved, because in the gel they don't fall apart, but they sink in and they are fixed, let's say. So this is a very neat way to do that. We deploy them typically for 24 hours. As you can see, there's at 3 depths there's this set of 4 tubes. Then we have a whole set of floats, and in the end a big float with a beacon that we can find back through a satellite signal. We know the coordinates. They typically float for 6-7 nautical miles. And after 24 hours we pick them up again and see what we caught. Sorry. We have to fill these tubes with seawater, obviously, which we densify a bit. We make it a bit heavier by adding salt. So here's a setup with a filter that we connect to the tap of seawater. With the filtered seawater, which is really clean, because we don't want any contamination, obviously. And this filtered seawater, we add a bit of salt to make sure that this water stays inside the tube when sinking down and when being recovered after 24 hours. Any questions? If not, then let's proceed into the lab, where Bob will tell you all about yet another way to collect dust using a buoy.
Ja, die mogen eraf. Ja, buitenboord. Eerst op een buitenboord? Ja. Mag ik nu even buitenboord? Ja, prima. Dan moet ze echt mogelijk zakken. Ja, dan moet ik even wegzetten. Oh, ja, stel je het vast. Dat zijn wel ja, dat is een auto. Oké.
Als je maar vooruit. Ik heb zo het licht aanzetten achterop en dan...
Ja, ik wil even kijken of het top is.
Oh, dat heb ik niet vet.
Well, hello. My name is Bob Koster. I work as a science assistant at the Ocean Systems Department, and I joined this cruise to assist with some of the scientific equipment. One of the pieces of equipment is shown here. So we have a dust collecting buoy out at sea. This dust collecting buoy can collect dry dust, but also wet dust. So it's the wet deposition, meaning when it rains, you want to catch all the rain, including the dust that's in the rain. And for that we have designed at NEOS an instrument, so it's called the wet dust collector. And basically what you see is a round cylinder which contains 20 sampling bottles. So it's a carousel that can rotate. And then we have a rain collecting funnel with a lid on top. And basically what it does, if it detects rain with this rain sensor, it will immediately open the lid. And then it can collect the rain with the dust in the funnel, and it will just go down in one of the sampling bottles. Well, basically the system can be programmed to in a way that you can choose how much water you want to have in a bottle before it switches to the next bottle to collect the next rain event. So I can make a small demonstration to see how it operates. So as soon as it would detect any rain, it will try to open the lid. And there's a small mechanism here, a spindle with an electric motor drive. And then it opens, and then it's ready to collect the rain. In the meantime, it registers the amount of rain, so you have more or less a quantitative measurements of how much water you collected. And when the rain stops, at some point it will just close again.
So what we're doing here is we take apart the buoy that was just recovered, and doing a lot of maintenance on the buoy. I already took some filters off. There's one filter left I want to show. Sorry. So inside the box there's a carousel with filters, 24 of them. One by one they rotate under the chimney, and now it's broken off, but here there's a piston that opens when the weather conditions are good. There's a whole setup of weather sensor and iridium satellite connection, and once the weather sensor decides that all conditions are met, the piston opens and a pump inside the box pumps air through the chimney into the box and over filters, which I'll show you how they look like after about 1 month. So I covered it to avoid contamination, but this is the typical orange color you see from Saharan dust, or basically any desert dust in the world. But this is a really nice sample, and I'm very happy with this result. I'll secure it in the lab. Alright, we'll continue disassembling the buoy, and this time we have a big maintenance setup because the batteries are going to be replaced. So there's these are the filter cups from the buoy. We have 24 of them. One by one they go under the chimney, and then air is pumped through. So this is really the dry concentration, I would say, not deposition, but concentration, because we're pumping air through a filter. And you can see the nice color of typical Saharan dust that at the moment we actually find in Europe as well, by the way. And what I'd like to emphasize, this is the dry material. We're also collecting rain, so there's recognized that the dust comes down with rain a lot as well. For this we designed this wet dust collector. And we have another set of 20 bottles inside the buoy, let's say. Trying to find a nice example of how you can see. So there's quite some material in here. The amount of water is less important because they have been standing in the buoy for quite a while, so some water may have evaporated. But what you'd like you to see is there's quite a considerable amount of dust in this tube as well. And we have no idea how much this is, how much dust comes down with rain. But it has major consequences because we think that the dust during the formation of rain droplets is already leached, because in those atmospheric conditions it can become really acid. So the iron, which you can see from the orange color, under conditions of lower than pH 1, the iron is already pre-treated, let's say, so leached off the particles and maybe made bioavailable for the plankton in the ocean. So when a rain droplet forms around a salt crystal or a dust particle, through convection it rises up in the atmosphere. In the atmosphere we have really acid conditions, pH can go below 1, and then that droplet moves up and down until it's heavy enough water has accumulated on that particle to fall down as a droplet, and by then the pH is again maybe around 6. Then it comes down into the ocean, and then the iron is maybe bioavailable. This is a hypothesis that we'd like to test. So a lot of unknowns still about this dust and the relationship to phytoplankton. Yeah, so 15 more to go. So the underwater part of the mooring has been installed already. Now it's time to deploy the buoy. We installed all the filters, the batteries, the programming, everything was alright. And as you can see, she's good to go for another year of sampling and monitoring. And do your best. See you in a year. Bye, Laura. You have to film this, of course.